Welcome back to another explainer. Today, we're pulling back the curtain on the invisible mechanics governing literally everything around us. From the sound of my voice to the light filling your room right now, we are going to explore the absolutely fascinating, often unobserved physics of waves. Think about the last time you dropped a pebble into a perfectly still pond. You immediately see those rings rippling outward, right? It feels totally intuitive to assume the water itself is flowing outward toward the shore. But is it actually moving? Like, is that physical water traveling away from the splash? Okay, let's dive into this. To find the answer, we'll go on a quick 5-step journey today. We'll start with the nature of waves, contrast transverse and longitudinal motion, break down a wave's anatomy, discover nature's speed limits, and finally wrap up with the mathematics of superposition. Section 1. The nature of waves and the illusion of movement. So we really need to redefine what we're actually looking at when we watch a wave move. Let's go back to that pond. If you were to toss a small cork onto the disturbed water, what actually happens? Well, the cork doesn't surf the wave all the way to the edge of the pond. It merely bobs up and down in the exact same spot. And this perfectly proves our fundamental definition. A wave is just a pattern of disturbance. It's brilliantly transporting energy and information from point A to point B, but without the actual physical transfer or flow of the matter itself. The water isn't moving away, only the disturbance is. Nature basically gives us 3 fundamental categories for these traveling disturbances. First, we've got mechanical waves. These absolutely require a physical medium to travel through. Think water, guitar strings, or the air we breathe. Second, there are electromagnetic waves, like light and X-rays. These are special because they can travel through the absolute vacuum of empty space. And finally, we have matter waves, which deal with the quantum mechanical behaviors of things like electrons and protons. Now, for today's explainer, we're going to focus primarily on that first category, mechanical waves. Moving on to Section 2, transverse versus longitudinal waves, where direction really matters. Let's explore how the actual materials of a medium behave when a wave forces its way through. Generally, the particles do one of 2 things. First up are transverse waves. Here, the material oscillates perpendicular to the direction the wave is actually traveling. It's like plucking a guitar string. The wave travels down the neck, but the string itself vibrates up and down. This creates what's called a shearing strain, which is why we mostly see this in solids. On the flip side, we have longitudinal waves. In this case, the particles oscillate parallel to the wave's path, creating compressive strain. This is exactly how sound waves travel through the air, creating little pockets of high and low pressure as they go. If that longitudinal movement is kind of hard to visualize, I absolutely love this real-world analogy. Just imagine a stationary train sitting on a track. When an engine bumps the very first train car, that push is transmitted through the spring couplings from one car to the very next, all the way down the line. The energy of the push travels the entire length of the train, right? But the whole train hasn't bodily moved down the tracks. Each car just gently nudged its neighbor. That perfectly visualizes how a longitudinal sound wave travels through air molecules. Section 3, Anatomy of a Wave, where we translate these concepts into math. Now that we've got a solid physical intuition for what a wave is, we need to translate this into mathematical language. And what's really interesting is just how simple the core spatial measurement of a wave really is. We call it the wavelength, represented by the Greek letter lambda. It's simply the minimum distance between 2 points having the exact same phase. So if you measure the distance from the top of one crust to the very next consecutive crust, or from trough to trough, you've got your wavelength. It is literally the fundamental physical length of a single wave cycle. But, waves aren't just frozen shapes suspended in space. They exist in time, too. And that brings us to the period, represented by a capital T, and angular frequency, represented by the Greek letter omega. If wavelength is our spatial measurement, the period is our time measurement. It is simply the time it takes for one specific element of our medium to complete one full up and down oscillation. And we mathematically tie that duration to the angular frequency using a really elegant relationship. T equals 2 pi divided by omega. By combining space and time, we get the displacement relation. Now, I know it might look like a slightly intimidating equation at first glance, but we can easily deconstruct it piece by piece. The y is just the exact displacement of our particle. The a right at the front, that's our amplitude, basically the maximum height of the wave. Inside those parentheses, k is the angular wave number, kx minus omega t, is the part that links our space and time together, and phi at the very end is just our starting point, our initial phase. When you actually break it all down, it's not scary math at all. It's just a highly precise map telling us exactly where any piece of the wave is at any given fraction of a second.
All right, section 4, the speed of waves and nature's limits.
Let's see how all this builds into nature's absolute speed limits. Before we even talk about physical mediums slowing things down, just take a moment to appreciate this massive number. 299,792,458. This is c. It's the constant speed of all electromagnetic waves, like visible light or radio waves, traveling through a vacuum, measured in meters per second. This right here is the absolute speed limit of the universe, and it requires no medium whatsoever. Mechanical waves, however, are a totally different story. They have to physically push their way through a medium, and their speed is almost always a tug of war between the inertial and elastic properties of that specific medium. And this brilliantly illustrates how different materials require completely different mathematical formulas just to figure out the wave speed. For example, the speed of a wave on a stretched string is derived from its tension and linear mass density. For a solid bar, you have to look at Young's modulus and the density. But when you get to gases, well, it gets a bit trickier. Isaac Newton originally theorized that the speed of sound in a gas just relied on pressure and density. But here's the catch. Newton's formula didn't actually match real-world measurements. He wrongly assumed that sound moving through air created isothermal changes, meaning the temperature remained totally constant. Enter the brilliant scientist Laplace. He recognized that sound actually causes rapid adiabatic changes in the air. Basically, the compressions happen so incredibly fast that heat literally doesn't have time to escape the region. By adding a simple correction based on specific heats, Laplace finally aligned the mathematical theory with reality and perfectly calculated the speed of sound at standard temperature and pressure to be exactly 331.3 meters per second. Which brings us to our final stop, Section 5, the principle of superposition, or what happens when waves collide. I really want you to imagine what happens when two separate wave pulses are traveling in opposite directions and inevitably cross paths. Do they crash? Do they bounce off each other? Break apart? The reality is actually wonderfully elegant, and we can track it chronologically in 3 steps. First, the pulses approach each other. Second, they overlap. And in that exact fraction of a second of overlap, the net displacement of the medium is the exact algebraic sum of their individual displacements, meaning if a crest and a trough of the exact same size hit each other, they will literally cancel each other out to 0 displacement for a split second. No way, right? But then, step 3, the pulses separate and continue on their way, completely retaining their original shapes and identities. So, the absolute crucial point here is that waves pass right through each other without being destroyed. They only add up or cancel out during that exact brief moment they occupy the same space. And that leads us to a pretty profound thought to end on for today's explainer. If waves move through a medium as if other waves aren't even present, what hidden patterns are passing right through you at this very moment? Think about it. Right now, you're sitting in a space completely flooded with Wi-Fi signals, radio waves, the faint hum of electricity, and the sound of my voice. Millions of individual waves all perfectly superimposing, mathematically overlapping, and passing right through your space. They're totally invisible to the eye, yet completely governed by the beautiful mechanics we just explored. Thanks so much for joining me today, and keep looking for those invisible mechanics all around you.